First of all, I would like to express our gratitude to organizers, and I'd like to present our small report, clusters models for generating capacities to identify optimal scenarios for Ukrainian power plants restoration. So the problem is that as a result of Russian aggression, it was one of the direction of this aggression was an attack to generation capacities and network capacities of Ukrainian energy system. And today the question of post-war restoration become very actively discussed. And one of the main topics of this discussion is the future of the coal-fired power plants, which traditionally was a big part of our capacities. It's important to find a balance between the decarbonization plans and ensuring low-cost production of electricity in this topic. So when we're talking about models for Ukrainian power plants restoration, we have analyzed some models of restoration, and traditionally in the basis of this modeling is the same models like for the power generation planning. But there are some features of the modeling process. First one is volumes and structure of electricity consumption. You understand that now it have changed significantly. So the sources of fuel supplies, for example, the coal or Donbass region now is a big question. Big damage of generating capacities, first of all, of thermal power plants, and future environmental requirements. To plan the development of power system with high share of RAS, it's necessary to work out new models for generating capacity development. And it's necessary to formulate them on the set of dispatching problem solutions, because renewable energy system significantly change the operation modes of traditional power equipments. The purpose of the study is to develop cluster model for generating planning, to form restoration scenarios, and to determine the generating capacity restoration effectiveness in the condition of Ukraine. The Topilska power plant was chosen for this research. This power station was severely damaged by a Russian military strike. It consists of 4 coal power units of 300 megawatts each and 2 gas oil power units of 300 megawatts. To analyze the working modes of the power station, you can see here the representative set of load weekly graphs was produced. Here you can see the summer typical load weekly and the winter typical load. 4 scenarios was worked out to analyze the recovery of Topilska power station. The first scenario, the basic concept of this scenario is the keeping of the existing coal and gas oil power units. Of course, these power units is worked out and damaged, so it will be necessary to modernize them and to implement environmental measures. So it's a SX and X removal and dust cleaning. Also, installation of open cycle gas turbine is possible in this scenario. The second scenario is adding of saving system, electricity saving system to the first scenario. The third scenario is a coal-free scenario. So according to this scenario, all the existing equipment will be decommissioned, and instead gas turbine and electricity storage system will be built. And the first scenario also without existing power equipment, but adding the combined cycle gas turbines to the open cycle gas turbines and saving system. Here I'd like to briefly discuss the structure of the model. Here you see the objective function is the sum of capital and operational costs. So you can see here the cost of production electricity, startup and shutdown costs. Also some limitation on the volume of investment, the condition of positive development, construction completion. Here you can see also the balance of production and consumption. So production of TPP, production in generation mode of ESS, consumer load and work of ESS in a pump mode. Operation cost of thermal power plant. The production cost is approximated by the polynomial function you can see here. Also, startup and shutdown costs are taken into account. The mode of operation is very important here, and it is described by the relationships of the integer functions. The limitation of current maximum and minimum attainable load is also taken into account. And also here you can see the description of ESS system, or the costs of ESS system operation, energy balance, and also some conditions of ESS system operation. Now take a look on the computational results of this experiment. You can see here results for four scenarios. Two first is the cost scenarios. Here you can see first scenario is 4 coal power units, any gas oil existing units, and also some capacity of open cycle gas turbines. The optimal for the second scenario is also 4 coal units, one less gas turbine, and some volume of ESS. And also 2 coal-free scenario. The third scenario is open cycle gas turbine and little bit accumulators, and fourth scenario is only combined cycle gas turbine. Here in the right you can see comparison of the costs. It could be named life cycle costs. It's a capital and operation costs for each of this scenario. The basic one is the first scenario, 100%, and you can compare to the first scenario or other. So the second scenario is more effective with accumulators. The third scenario without gas and only open cycle gas turbine is twice more expensive, and the scenario with combined cycle gas turbine is 30% less effective than coal scenario. Now let's take a look on some features of these scenarios. First of all, the first scenario, it's a coal scenario. So all 4 coal power units remained in operation because of very low fuel costs. Gas oil units, 3 megawatts existing, are decommissioned, and in addition 5 open cycle gas turbine are put into operation. Here you can see that gas turbines covers the peaks of load. Here you see, but better to take a look here. It's different between load and the load of consumers and load of coal power units. And here in the winter time, this is more presentable, this difference. So because of existence of gas turbine, the coal power units working in the more stable mode. The second scenario is adding of energy-saving system accumulators to the first scenario. Here you can see that also 4 power units are in the operation called power units. One less OCGT are put into operation, and additional 175 megawatts of accumulators is built. According to the modes of operation, the operational modes of coal power units become more stable than in the first scenario. Here you can see the blue line is operation of gas turbine, and green and violet lines is operation of accumulators. The next scenario is a low carbon or coal-free scenario. Here 14 gas turbines are put into operation, and the putting into operation of accumulators is very low because gas turbines has very nice maneuver's capacity. And the load of gas turbines practically the same like a load of consumers. Here are the accumulators, like in summertime and winter time. But the cost of this scenario is 95% higher than in the first basic cost scenario. In the first scenario, we adding very effective combined cycle gas turbines. The effectiveness is about 57-58%, and only 4 combined cycle gas turbines are introduced. Any OCGT or accumulators are not introduced. The reason is that high specific capital costs of combined cycles are fully compensated by their very high efficiency. And compared to the basic cost scenario, the life cycle cost is 33% higher. Okay. And conclusion. Restoration of Ukrainian power plants requires analyzing of different technological scenarios of their future development, and for this reason it's necessary to work out the special models. We worked out the long-term cluster models, which take into account the main technological and economical characteristic of the generating equipment and energy storage system. The suggested model was were used to analyze the restoration scenario of Trubizka power plant, and the results are very important, I think. Thank you very much for your attention.
Thank you. Thank you for your presentation. Do you have any questions, colleague? No one. Okay, thank you.
Oh, thank you very much.